Hey everyone, this is Kushal Shimali and thank you for visiting my YouTube channel. So in the past, we have used face detection in a lot of applications and a lot of users came up to me and said, how does it work? So this YouTube video is dedicated towards learning how does it work in OpenCV. So I came up with this research paper, like I found this on the OpenCV documentation. It's called Rapid Object Detection using Boosted Cascade of Simple Features, right? It was authored by Paul Viola and Michael Jones and accepted in CVPR in 2001. So this paper was accepted in 2001 and right now I'm recording this video in 2020. So it's been quite a lot of time, right? And we have been talking about deep learning in this decade, but this paper uses machine learning and it's kind of surprising for others, but for me it's completely makes sense because even though deep learning is there, but machine learning has not gone, right? And we're going to talk about what contributions the authors have made from this research paper, and we're also going to talk about what is the methodology behind face detection in this Viola-Jones algorithm. So let's go ahead and talk about it. This is going to be a YouTube video series, like there may be part 1, part 2 and part 3, because in just one single video it might be a lot for you to digest, right? So make sure that you watch the other parts of the videos as well when they are out, and if you like the content, please like the video and subscribe to my channel. Let's go and talk about this research paper now. So what are the topics we're going to talk about in this video? The first thing is we'll be talking about the key contributions of the paper. It's very important to talk about what the authors have contributed to the field of computer vision. That is the first thing we have to take care of, and it's going to be really interesting because whatever they have discussed, we'll be talking about them one by one. So the first thing after this is going to be about what are the rectangular features and why use them over pixels. I know this term will be very new to you, so just consider rectangular features as just some kind of features which we are using because it's a machine learning problem statement, right? So we are using some kind of features. And what is an integral image? How does it help us, right? Why use an integral image and why not just an original image? So we'll be talking about what is it and how does it help and how to calculate it and use it for calculating the rectangular features. So let's go ahead and talk about the contributions first. What they have contributed to the field, right, is really important. And if you see, I've made the first point bold because that is the point we're going to focus in this video, is that they introduced integral image for object detection. So do not forget that this research paper was for object detection. They narrowed it down to faces by using the dataset of faces for this problem statement, right? And faces are just like objects, right? My face is an object for the machine, unlike human beings. So introduction of integral image was done by these guys for object detection. It has been introduced before for graphics as well, but then for object detection, these guys introduced integral image for that. The next point is learning algorithm based on AdaBoost. So that's why that's the place where machine learning comes in. AdaBoost is just a learning algorithm, right? And they used AdaBoost learning algorithm for this machine learning problem statement. And the third point is they use cascade of filters, right? So cascade of filters means one filter on the top of other and so on, right? So there are stages of filters and that's what we call cascade. So we make a cascade of filters and we use these cascade of filters to remove background features. So what they did is, suppose my face is just the basic foreground and everything else is the background. So you use these cascade filters to remove the background features. Right, so let's go ahead and talk about very basic stuff called integral image and rectangular features. So we'll be first talking about rectangular features, that's more important, right? And let's go ahead and talk about what are the rectangular features. So we'll be talking about what are rectangular features and why use them over pixels. So think about this, right? If you see a face, right now you are seeing me, and how do you recognize a face? Like if this object is a face or not, how do you recognize? Sometimes you just notice eyes in it, sometimes you notice nose, or at times you will notice if there are ears around it, right? Or if there's a color difference or different things, right? But this should work for all the ethnicities, for all the races, for all kind of people, right? And like I'm on a darker side, so it should work for me. For people on the lighter side, it should work for them as well. So machine learning should understand all different kind of faces, and that is more important. So let's go ahead and talk about how does it accomplish this task and what are these rectangular features. Right, so if you see in this image, right, if you see this image on the left, we are having some example of rectangular features, right? And these are just examples from the trained model. So these features were generated from the trained model, and if you see the sum of the pixels which lie within the white rectangle are subtracted from the sum of the pixels in the gray rectangles. Now if you can set a threshold and if you find some value from there, the machine learning model will try to understand from the difference between those rectangles if there is a positive case or not. So based on a lot of results from all of these features, they will classify a window as there is an object or not, okay, inside that window. So there can be a lot of rectangles in a single filter, right? So as you can see, like in the figure 1, in the figure A, subfigure A, you can see that there are two rectangles. One is white, one is gray. And in the subfigure B, you can see that there are again two rectangles, but they are adjacent vertically, right? So the top one is gray and the bottom one is white. So you can calculate the difference between the sum of the pixels in the gray rectangle with from white rectangle. So whatever the difference is, you use that difference to classify whether there is any positive case, whether there is an object, any chance of an object being there, which is our, like in our consideration, it is a face. So similarly in figure C, you see three rectangles, right? And imagine that here, right here, okay? So you have one eye over here, right? And one eye over here, and there's a nose in between, right? So it's kind of a three rectangular feature case where you have the difference between left eye and the right eye, right? And in between this rectangle, so there should be some threshold value where we can set, because usually the eyes are on a darker side, and this will be the intensity wise will be some difference. So if we can use this in any case, in any way, to classify whether there is a chance of a face being there or not, then it will be really helpful for us. So these are the rectangular features which were used by Viola Jones, right? In the right figure, you can see that from the input image on the bottom left, there were these rectangular features which were, calculated by the model, right? And on the top, you see those rectangular features were the ones, one of the, features which were found out. And you can see one of them is a two rectangular feature and the other is three rectangular feature, right? So we'll be using these rectangular features to find out whether there's a face in it or not. So this is a very basic application, right? And that is why it is only useful for frontal faces, for faces which are, inclined towards different direction, or, different faces which are not frontal facing. It will not work for them, okay? It will mostly not work for them, right? You might be lucky if it works. Anyways, why use them out pixels? That's the one of the most important point. Because you have rectangle features, you have pixels. Why use these rectangle features? Why use these three rectangle features? Why use two rectangle features over the intensity values at each location, which are in fact called pixels, right? So the thing with these rectangle features is it gives you a domain knowledge. So think about a face detection task. These rectangle features will give you an idea that there is a chance of two eyes being there and a nose for the three rectangle feature, right? You remember we talked about one on the left, one on the right, and one in the middle. There were three rectangles in that feature. So it gives you a domain knowledge about this problem statement about face detection task if you use rectangle features. If you would have used just pixel values, right? What does it give? What does a value of 100 at a location 10,10 in an image give you? Like what kind of knowledge does it give you about the task? It doesn't give any domain knowledge. So these rectangle features help the model to encode all the domain knowledge into this, into this model. But there's another point of this, right? This makes the computation much faster. So think about a film star, right? Think about a movie star. Now they usually have an HD, they usually have a HD image of themselves, right? 1920 cross 1080 cross 3. That means the width is 1920, maybe height is 1080, number of channels are 3. That means the image is RGB. So the total number of pixel values are like huge. And if you start computing over pixel by pixel, it's going to be like computationally expensive, right? So you cannot operate on all those pixels one by one, right? So it's always better to have some features over which you can compute and find out whether there's a face or not. So it just increases the computation time, it decreases the computation time, and that's going to be really useful. So let's go ahead and talk about integral image, which is one of the most important things in this research paper. It's basic, but it's really important. So this integral image, the first keyword is itself, signifying about the whole integral image word. Integral, by that always we mean finding sum, right? So think of an original image. What do? At any point location x comma y, right? At any point of location x comma y, the integral image will be what? Sum of pixels above, left, and at x comma y. What does it mean? If you have a location x comma y, let's say 10 comma 10, so it is going to be sum of all the pixels above 10 comma 10, right, and on the to the left, right? So it's going to cover all that area above and to the left, and including itself, right? So it's inclusive. So that's also important point. So you can just formulate this in this way, that double I x comma y, double I is for integral image, is going to be a sigma from x dash, which is like all of those which are less than or equal to x, and for all points which are less than or equal to y, and just sum all those values, and that will be our integral image at location x comma y. So it's really easy concept if you try to visualize it, which we will be doing in future slides. But for now, just try to get this concept that this is what integral image is. The next question is, of course, why integral image? How does it make sense? You have an original image, why to have another image called integral image? Why have so many images, right? And one of the thing is, it can be computed in just single pass, right? So once you have this integral image in just single pass over the original image, you can compute all these rectangle features, hand-like features in constant time, right? So that's one of the most important thing. To reduce the computation time, you need to have something, and one of those things is integral image. The next thing is the calculation of the calculation of rectangular features is really faster when we use integral image, right? But how and the how of both of these points we're gonna talk about in the next slide. So let's go ahead and talk about how is it computed in one single pass over the original image. So this is the formulation, because the machine will not understand the intuition behind integral image, right? So you have to give it some formula to find out what is the integral image. So these are the two basic equations which are used to find the integral image. The first, x of y, is basically the cumulative row sum. In this case, you can think of all the sum of all the pixels which are above it. Okay, that's going to be the s of x comma y, and I x comma y is simply the integral image, right? So but do make sure that you note this out, that s of x comma minus 1 is always 0. I'm going to talk about it right now, because you think any point which is on the top row, right, the sum of pixels above it will always be 0, because there is no pixel above it, right? So what we do is we say that s of x comma y is always the pixel point at that location, if that location is in the top row, right? If you don't understand this right now, we're going to talk about it in the next slide. Right now, just note these formula, because we're going to use it for calculating integral image in one single pass. So let's go and go to the next slide and talk about it. So in the left figure, you can see one matrix, right? Image is a matrix after all. So imagine this as a grayscale image, right? And it's going to be a 2D matrix. Each cell right now in this image denotes the location of that pixel, right? So for example, that is 0 comma 0, right? Here it is 0 comma 0, here it is 1 comma 0, here it is 2 comma 0. So this is what it denotes. It doesn't denote the pixel value, right? It can be anything. Now think about this. You will get the integral image in one single pass. That means you will iterate through each pixel only once. Okay, so let's start iterating. Okay, so we'll be iterating through 0 comma 0 first. That's the origin, right? 0 comma 0. So let's start with location 0 comma 0, and in the right image you can see I've done it for 3 locations. So if you take a look at 0 comma 0, and if you remember the formula, right, what is going to be s of x comma y is going to be s of x comma y minus 1 plus I of x comma y. Now I told you guys that s of x comma minus 1 is always 0. Why? Because there is no pixel above it, so the cumulative row sum above any pixel is always going to be 0, right? So what you do is s of 0 comma minus 1 plus I of 0 comma 0. Now you can just make it 0, the first term, that means s of 0 comma minus 1 is 0. So from here you get only the pixel value at 0 comma 0. That means the cumulative row sum for 0 comma 0 is the pixel value at that point itself. Now what is going to be the integral image at 0 comma 0? You have the cumulative row sum. All you need to do is find the integral image left to this point. That means IA of 0 minus 1 comma the y coordinate will stay the same. Okay, so all that is, like I have discussed this before as well, IA of minus 1 comma y coordinate can be anything. If the x coordinate is minus 1, then you have to put it to 0, because there's nothing like IA of minus 1, right? The integral image at minus 1 is there is nothing. So that's what you get. So it's going to be 0 plus s of 0 comma 0. Now we talked about it first. S of 0 comma 0 is what? The point itself, the pixel value at that point itself. So it is what? I of 0 comma 0. I is the original image. So from there you get the integral image at 0 comma 0 is the point itself, is the pixel value at that point itself, right? But what about 1 comma 0? So that is the first iteration through that location. So you only iterated once through that 0 comma 0, and we have found the integral image of 0 comma 0. Next thing, for location 1 comma 0, how do you find, right? But let's talk about the intuition here, okay, in a formula. Now think about this. I said the integral image at location x comma y is the sum of the pixels above and to the left of it, including that point itself. Okay, so if you take a look at 1 comma 0 in this matrix here, what are the points above it? There's none, like there's no point above it, right? That's the boundary of the image. And what are the points left to it? There's only one point, 0 comma 0. And I said that including the point itself, that means the final integral image for 1 comma 0 should be what? The pixel value at 0 comma 0 plus the pixel value at 1 comma 0. So here you can just see and see the final output, that is I of 0 comma 0 plus I of 1 comma 0. That is the final output as well. So intuition wise, if it is clear to you, you can always do the formulation and it will be more clearer to you once you start practicing. Okay, so this is how you calculate the integral image in just one single pass. As you see that I have only iterated once through each pixel value, each location. So you will get the integral image at each location in just one single pass. But how does it help in calculating rectangular features, right? You have the image, what's the pipeline? You will have an image, you will get some features from it, right? If the image is in the training data set, you will get features from there, and you will try to find the error after your learning algorithm is done, and you will try to find the error and optimize it further, right? That's how machine learning pipeline works. But how does it help? How does integral image help instead of using original image? Why not use pixels? Why not use original image, right? The point is to find the differences between the sum, right? So we talked about it. We had rectangular features, we had 2 rectangle feature, we had 3 rectangle feature, right? So there, what we were doing, we were trying to find the differences between the sum of between the sum of pixels in a rectangle. Okay, understand this. We had a 3 rectangle feature, one rectangle in this right eye, one rectangle in this left eye, and one rectangle between these 2 rectangles, right? So we had 3 rectangles. Now for this, we have to calculate the difference, like we have to sum these 2 rectangles and subtract it from this middle rectangle, right? So for that, you have to calculate the sum of the pixels in each of these rectangles, and then you have to find the difference between them. So this difference and sum of these pixels in a rectangle becomes really fast if you do it using the integral image. And this is what this slide is about. Okay, so how does it help? Remember this, that it helps by making it faster. What does it make faster? It makes the subtraction and the summing of the pixels in a rectangle really fast. And how does it help? I'm going to tell you now. Okay, for now you just take a look at this image. Okay, this is from the research paper itself. Okay, I have just written something over it. So you have these rectangles, right? A, B, and C and D, right? At locations 1, 2, and 3 and 4. Okay, and this is similarly, like you have to find the integral image at A. What is going to be is sum of all pixels in A. That's clear to you because there is no pixel value to the left of rectangle A. There is no pixel value to the top of rectangle A. So it's going to be sum of all pixels in this rectangle A, right? What is it going to be for location at 2? That means the rectangle B is going to be sum of all the pixels in B plus integral image of A. That means sum of all the pixels in A and sum of all the pixels in B. Okay, what about C? It's going to be same, right? To the top of it there is a rectangle A, so that means integral image at C. For C is going to be integral image at A plus sum of all pixels in the C itself, right? But what about D? So what about D? If you see here the fourth point, integral image of D is going to be what? Integral image of A, but there is a negative sign to it, okay, remember, plus integral image of B and integral image of C and sum all the pixels in D. Why did we subtract integral image of A? Because for B and C we already had A over there, right? Because integral image of A had all the sum of all the pixels in A, right? Integral image of B had integral image of A as well. Now integral image of C also had integral image of A. So if you sum B and C twice, if you sum B and C, you will get integral image of A twice. So you have to remove one of that, right? Just trying to find a union, right? You remember you have to separate one of those rectangles at least once. So that's what we are doing. So we sum up integral image of B and C and we separate integral image of A and we add up all the sum, like we add sum of all the pixels in D, right? But the point is, as I told you, for 3 rectangular feature, you have to subtract sum of pixel of these 2 rectangles from the middle rectangle. That means we are doing subtraction. So for that, you first need sum of the pixels in that rectangle, right? So what's the formula for sum of pixels in D? It's simply going to be D plus A. That means the integral image of D plus integral image of A minus the sum of integral image of B and C. So you have found the sum of pixels in D just by using these 4 values, that's the integral image, right? And if you want to subtract 2 rectangles, for that you need just 6 array references, okay? If you think of 2 more rectangles to the right of 2 and 4, you will understand that all you need is 6 array references, that means 6 integral images to calculate the difference between sum of 2 rectangles, okay? Similarly for 3, you will all you need is I think 8 array references, right? So this just goes on and this is how it helps. So we'll be talking about this in the next video, but to understand how does it help, it makes the subtraction of sum of rectangles in a rectangular feature really fast, okay? Because you have less array references, and as I said, once you have the integral image, everything will be in constant time. So it really helps a lot. So in this video, we talked about integral image, we talked about rectangular features, but in the next video, we're going to talk about AdaBoost learning, how does it help and what kind of different approaches the previous researchers have made. So make sure that you check it out as well once this is out, okay? And also I'll be going live on YouTube. I regularly go live on Saturdays and Sundays on this YouTube channel. So make sure that you join me and I'll be talking more about this YouTube video, how does it work, and I'll be solving your doubts in that live stream. So maybe if you're if you're too late, so you will always have a chance to rewatch that live stream, and I will try to add timestamps for that video as well so that it helps you out. If you like the video, please like the if you like the content, please like the video and subscribe to my YouTube channel. Make sure that you spread it so that it helps a lot of students out there who are trying to learn these things. And thank you for visiting my YouTube channel. Hope you have a good day.